What we're going to do today, we're going to focus on the human brain. I'm doing this for a number of reasons. As I mentioned before in lecture 1, we need to study the human to be able to design good interfaces. And this course also focuses on HCI research, trying to prepare you to be HCI researchers and trying to give you in-depth knowledge about what is possible in terms of hardware and software that would benefit the human. So even if you're not going to become an HCI researcher in the future, you still need to understand what is the potential of technology in terms of helping humans to enhance their quality of life. And there is nothing more of a buzzword nowadays than brain-computer interfaces. Lots of people are claiming lots of things, and the goal of this lecture is to give you an in-depth look into the human brain, and we will discuss what is possible, what is still not possible, and what is science fiction towards the end of today's lecture. So let's move on. Brain-computer interfaces became a sensation with this video. I invite you to watch it on YouTube. It's a game made in a Scandinavian country called Brain Ball. The idea was quite simple. The two players who play the game compete in controlling their stress. So the ball moves to the player who is less stressed. Stress was measured using what we call an electrode, which is a thin wire placed, in this case, at the front of the head, measuring the stress level. The game was a sensation for a number of reasons. This was several years back. First, how it's made. The ball is made of metal and it's moving in air because there is a magnet underneath the wooden table that moves it. So it looks fancy. And second, it was being played by thinking, or actually, in fact, controlling your thinking if you'd like. And people have never, or the general public have never seen anything like this before, so it was quite a sensation, and it kind of brought brain-computer interfaces into public awareness, that we could, understand how people think, which is completely flawed. This is still not possible, but people claimed or argued, you can see this video, they can know what you think of, and that's again inaccurate. Okay, so we will see really what's the reality. So I invite you to watch this game. It's very entertaining, and the one who is actually less stressed will actually win at the end. Now let's go to reality. The area of brain-computer interfaces started when a group of electrical and electronics engineers decided to build a headset that would be mounted on the head of someone who's completely paralyzed to help him move a wheelchair. This was way back in late 1970s, and this area is still active and mostly dominated by such groups of researchers who are trying to help people who are disabled. Now, by now you must have seen something like the image I'm presenting here. Either you've seen it in science fiction movies or you've seen it in the news. Okay? Notice here that the kind of actions the user is making is quite simple. Let's go forward, turn right, turn left, stop, or perhaps rotate and go in the reverse direction. Otherwise, there's nothing. And there is a reason why, as you will discover, we can only do a handful of things. Okay? The idea was we're going to record signal from the brain from which somehow we know what is the user intention. Remember that a user who's completely paralyzed could even be paralyzed at the level that he cannot talk, he cannot express himself using his tongue. Neither he can move any of his arms or legs. So if we can know the thinking, then we can help him. Okay? This is really why brain-computer interfaces started. It wasn't about knowing how people think, it wasn't about knowing how to enhance people thinking, but actually how to help people who are disabled. Another sensational piece of news that also caused a lot of hype and perhaps some confusion was this article that I have put for you here to read about this lady who was also completely paralyzed, who had an implant, an electronic chip planted into her brain, and the electronic chip recorded her intended motion. This is what's called intended motion. Now, intended motion means what she intends to do with her arms or legs or feet or neck or even her mouse movement. And the motion was captured and passed to a robot that will do the motion that she intends. So again, we will cover today how is this possible and what are the limitations of this. Okay? Another very popular application of brain-computer interfaces is what's called dispellers. What you see here is a grid of letters that are flickering very fast, and using a technique, very, very basic and simple technique, we can know which letter the user is trying to type. Looks very ambitious, but it's actually a very primitive technique in the sense that it's extremely slow. So you cannot, for example, use this to write. You will write much faster by typing on a keyboard. But for someone who's completely paralyzed, it's better than nothing because they cannot move their hands or their arms or their legs or their feet or their tongue. So that's the only thing probably you can give them so that they can start writing. Okay? So we will talk about this again later on. Now, if you have heard about BCI, you probably, because you have seen one of these headsets. So these are new commercial headsets for playing games. They record your brain signal and they enable you to play a game. Okay? So this is actually one of the really breakthroughs that we have seen in recent years related to BCI. Historically, the price of these headsets was beyond the capability of an average user. Most BCI or EEG or headset recording devices, if you'd like, we will detail about them shortly, were in the hundreds of thousands of dollars. Nowadays, you can buy one of these headsets with few $100s. However, you must know that they are of low resolution and low quality. To get the real ones, you need to pay lots and lots of money. Okay? But it has brought BCI into the gaming domain. And this is an important step because that means there will be more money directed to BCI research and BCI applications. Because as you know, gaming is a very, very lucrative market with billions and billions of dollars. So it's a very important step towards popularizing BCI applications and enabling BCI applications. So I won't be surprised in the coming 5 years if you can buy an off-the-shelf BCI headset that you connect to your Android phone and do certain things with it. Now, another interesting aspect of BCI that it enables us to detect emotions. So this is actually one of the easy things, to your surprise probably, that we can detect, at least the basic emotions. So we'll talk later on. I have a portion of a lecture about emotions, but if you think of the basic emotions like being happy, being angry, being stressed, being disgusted, you can actually detect that relatively easily using the BCI headset, even a commercial one. Okay? So let's shift to the brain and try to understand how the brain works. Now, the brain, or the gray matter that you see on in the left image, consists of billions of neurons. These neurons are all connected together. So to give you a sense of how complex the brain is, or the human brain is, the brain has an average 1 billion neurons. Each neuron has an average 10,000 connections to neighboring neurons. So it's a massive 3D mesh of connections. The connections are done by the wires or the parts of the neurons touching each other. It's almost like an electrical circuit, but it's a huge electrical circuit. And it's indeed an electrical circuit in the sense that there is current in the brain. There is electricity in the brain. But it's so small that it won't fry your brain, okay? You can't even use it to light a bulb, even a small bulb, because it's all in the microvolts. But it is actually electrical current, which is, if you would like to reflect on it, very interesting discovery, because what we have been inventing in computers, which is processors and CPUs and so on, is actually a mirror image of ourselves. You understand that in the computer, the most important piece is the CPU, the central processing unit, and it consists of transistors, and there are billions of transistors nowadays in a single CPU. Well, the brain is actually even more complex than that, and it's just like it has the equivalent of transistors. Okay, so in the transistors world, everything is expressed in 0 and 1. Here also we have 0 and 1. 0 means no connection, 1 means there is a connection between two neurons. Okay, so it's an electrical circuit. To measure what's happening inside this electrical circuit, we're going to use a superconductor, typically gold or silver. We attach it to the brain or to the skull of the user, just like you see in the middle image. The researcher is trying to attach a specific electrode. First, he mounted a swimming cap that has holes made in it, and then you put the electrodes in these holes just to hold them steady. And using superconductors like gold or silver, you can actually capture the electrical current that is appearing on the skull of the user. If you try to plot it, you will see what looks like an electrical current, except it's very, very small. Now, you see down in the chart at the left, it vibrates up and down, above and below the 0, so it looks like an AC current. Okay? Now, what you see at the far right is an amplifier. When we record from the brain, the signal is so weak, we cannot really manipulate it directly unless we amplify it. So an EEG machine, EEG stands for electroencephalography, is nothing but a bunch of electrodes and an amplifier. Just like the amplifier you have if you have one in your car. It just amplifies the sound. This one is amplifying the electrical current. Okay? There is one catch. It is difficult actually to capture very weak currents. So we would use a solvent, which is basically water, added to it some free-moving ions, like for example sodium chloride salt, and we would put few drops under every electrode before it touches, or at the place where it touches the skull, so that we can capture the signal out. Okay? Now, notice that the brain is actually a 3D object. Its weight is about 1 kilo. Its size is about 20 centimeters by width of about average of 12 centimeters and a height of about 6 to 8 centimeters. Now, so it's 3D. It's a physical. It occupies a physical volume. What we are recording from is at the surface. So we are recording the resultant of a lot of electrical activity, but it's enough to learn a few things about the brain. Now, researchers developed a map of recording points. It's called a montage. The most popular, there's a number of them, the most popular is what's called the 10-20 montage, which is what you see in the chart at the bottom right. So the neurons, which is the N at the top of the chart, is the user knows. And if you calculate by angle, 10 angles, 20 angles, 20 angles, and so on, and then you go towards the center of the brain with, again, known angles, you actually can approximately find the locations for the different holes you have to make in the swimming cap. The reason why it's important to follow a certain map of recording points is because researchers wanted to compare their findings and have a universal standard for recording points. So usually those points are picked, or the 10-20 montage was picked to record from interesting areas in the brain. So we know about different areas in the brain, and we know that if we would like to learn about one piece of information, we better record from this specific point. So the 10-20 montage was found to be the most acceptable map of recording points because it covers all the interesting areas in the brain. Now, what you record in the brain or from the brain is what looks like an AC signal. Now, this AC signal, if you remember from your physics days, have some frequency, have some fluctuations. Based on the type of the fluctuation, whether it's slow or fast, scientists have came up with a classification system. They classify the signal to 5 bands. That's what they are called. The slowest one is the delta, followed by the theta, followed by the alpha, followed by the beta, followed by the gamma. Each one of those represents a range of oscillations. So 4 Hertz means 4 oscillations per second, 8 Hertz means 8 oscillations per second. So any wave you record that is between 4 and 8, so 4, 4.1, 4.2, 4.3, all the way till 5, 5.1, 5.2, all the way till 6, 7, all the way till 8 will all be called just theta. Okay? And the same thing for alpha, beta, and gamma. Now, why these divisions? The divisions are because every activity and every user state was found to be associated with a certain brainwave type. So for example, when you're asleep, regardless of where we record from, which point, which electrode location, okay, most of the electrodes, if not all of them, will show delta waves, which means your brain is slow, which makes sense because you're asleep, you're not really thinking. If you start to dream while you're sleeping, the delta will change to theta, the brain waves will become faster. Okay? Now, every activity has an associated set of waves appearing in certain locations in the brain, in certain electrodes. And this is actually the product, what I'm telling you, is the product of tens of years of research. So nowadays we know what is called the signature, the brain signature of many activities. So for example, if you're solving a math quiz and the quiz is difficult, we know where to expect to see the gamma, because gamma means you're really stressed. Okay, we know which electrodes, which locations in the montage, which recording locations will exhibit gamma, will show up gamma, okay? And so on. So the brain waves are actually quite important, okay? The takeaway is that the brain waves is divided to 5 types based on frequency range: delta, theta, alpha, beta, and gamma. Each wave type is associated with a set of tasks, functionalities, modes, user status, and so on. Now notice that from one electrode, we said we are recording an AC signal. And if you remember from your physics and signal processing course, a AC signal is often described as a composite signal. It has many signals inside it. And one of the main tasks or steps when we do brain recording is to do what we call decomposing the signal, which means extracting the little pieces from the original. So the original is what you see on the left side. I will decompose it using a mathematical technique like fast Fourier transformation or wavelets or independent component analysis or principal component analysis. There are many techniques, and I will get the individual signals from it. Okay? If you have not taken the signal processing course, don't worry a lot about it, because I don't actually require you in this course to do an EEG analysis activity. Now, the first step in EEG analysis is called signal decomposition. This is what we were just describing. Okay, signal decomposition, decompose the captured composite signal from each electrode to some constituent frequencies. So what you get out from the signal decomposition is how much of each frequency you have, or what are the frequencies you have, okay? Maybe you have a frequency of 2 hertz, which means you have a signal that oscillates 2 times a second. Or you have a frequency of 10 hertz, which means you have a signal that oscillates 10 times a second, and so on, okay? What we do is we sum up all the frequencies in a certain band. What do I mean by sum up? What are we summing up? We are summing what's called the power. Now, the signal processing part produces what frequencies exist and what is their power, which means what is their percentage to the total. So I might get a number like, you have a 3 hertz signal, which means you have a signal that oscillates 3 times a second, and its power is 7, okay? You can imagine this for simplicity as 7% of the total, okay? Or you might get, you have a signal that's 22 hertz, which means it's oscillating 22 times a second, and its power is 15, which means it's 15% of the total, okay? I'm just simplifying things here a little bit, just that you understand the essence of the word power, how much of that we have, okay? What we're going to do is, we're going to sum up the powers of every band. So the signal decomposition is followed by a power summation, so that I know how much delta I have, how much theta I have, how much gamma I have, and so on, okay? And then I will talk about the power of delta. I will not talk about, I have a signal that's 20 hertz and its power is 2, okay? That is not really scientifically interesting. What is interesting is to say, I have delta and its power is so-and-so. I have gamma and its power is so-and-so. But remember, each one of those is actually a band of powers. When we talk about theta, for example, it goes from, say, 8 to 12. So we have many inside it. We have 8, we have 8.1, we have 8.5, we might have 8.7, I don't know. But we have things from 8 to 12. So we're going to sum up the powers of what's inside this band and talk about the theta power. Now let's move to the anatomy of the brain. The brain has 4 distinct areas called lobes, plus a special area called the motor cortex in between them, okay? It also exists in an area called the central sulcus, which is, you know, either you call it the motor cortex or the central sulcus. It's the same thing. It's just depending on the speciality here, who is describing it. If it's a medical student, will probably tell you it's a central sulcus. If it's a cognitive psychologist, will probably tell you the motor cortex. Okay. Now, what's interesting is each area, each lobe, is responsible for certain functionalities that was discovered by researchers since EEG recordings started. Okay. Now, also very interesting, each area, it's almost like it has hundreds of processors. Every processor is dedicated to do one program, which is something specific the brain is doing. So for example, if you're designing 3D models, there is an area for manipulating 3D figures. And that area, we think of it as if it's actually a processor. Okay? So we have a processor for manipulating 3D models. You have a processor for writing. You have a processor for emotions. You have a processor for imagining things. You have a processor for memorizing things. You have a processor for writing prose or poetry. Okay, there's processors for everything you can do as a human being. Okay, now even more interesting is that the processors cooperate together. It's almost like a computer network. When one of the processors is overloaded with work, he can borrow processing capabilities from neighboring processors, and they all join together in one activity. That's if you put the user under stress, okay? And then when the activity finishes, the processors kind of separate themselves from each other, and now they're going back to the original mode, okay? So it's almost like, if you'd like to make an analogy here, to cloud computing. You need more resources, you get more resources. You don't need the resources will be taken away from you. So here in the brain, it was discovered that we have the same thing. So here are the four lobes. The frontal lobe is the center of intelligence. Okay, this is related to mathematical intelligence and logical intelligence. Okay, the occipital lobe at the back is responsible for processing what you perceive. So remember, when we talked about the eye, we said that the optic nerve exits from the eye, goes to the brain. The optic eye ends up somehow in information inside the occipital lobe first. So this is the processor for making sense of what you see. Not making sense as I mean by understanding it, but I mean by putting the pieces together, connecting the dots and the lines to make an object. And then later on the frontal lobe would decide what is this. Okay? Now, temporal lobe is for encoding and decoding of information. Parietal lobe has a number of jobs, including maintaining your balance. So let's look at each one of them. Oh yeah, and before I forget, the central sulcus is the black line that goes from the top to the bottom. It basically extends from the top of your right ear to the top of your left ear. Let's look at them one by one. The frontal lobe, okay? This is the center of intelligence. This is how when you think of something, this is actually what is active. This is what you use to concentrate and attend to pieces of information, okay? This also holds a lot of your personality and emotional traits, okay? For example, there is an area for emotions in the frontal lobe that was found to be generally a little bit bigger in females than males. And that's why you would notice that regardless of the culture, regardless of the place on earth, females are a little bit more emotional than males, okay? This has to do with that area being slightly bigger, not much bigger, but just slightly bigger between the two sexes. The parietal lobe is responsible for processing the sensory input, anything you perceive, okay? If you think of you seeing something, we said it goes from your eyes through the optic nerve to the occipital lobe, and then it gets moved to the parietal lobe to make sense of it along with the frontal lobe, okay? It's also related to body orientation, you maintaining balance. So if you think of yourself climbing the stairs or running or swimming, anything where you have to balance your body parts, the balancing activity is done inside the parietal lobe, okay? The temporal lobe was thought for a very long period, about 60 or 70 years, that it is actually your hard disk. It is your memory location. And it turns out actually that it is not entirely true. It's actually where the information is encoded and decoded, and the information that you store in your brain is stored in many places, not just in the temporal lobe, okay? It's also related to any behavior that you express. It has to do with your temporal lobe, as well as language processing and speech. Now, the occipital lobe, as I mentioned, is the lobe that processes the inputs from your senses. This includes your eyes, your ears, if you smell something, if you hear something, and your nose, if you smell something, and your skin, if you touch something. All this information is delivered through your nervous system to the occipital lobe so that it can put it together and present it to the frontal lobe to make a decision about it, okay? So if you touch a surface and it's extremely hot, it goes from your skin to your nerves to your occipital lobe to your frontal lobe, that actually you need to raise your hand immediately from that hot surface. Now we go to the very important one, which is the motor cortex. As I mentioned, it extends from your top of your right ear to the top of your left ear. The motor cortex, okay, is a very interesting part for BCI researchers and for BCI works. It is what is most commonly used in doing any BCI related activity because first of all, it's easier to record from. The reason why it's easier to record from compared to any other place in the brain is because what this has is clear divisions of regions where every region is responsible for the movement of a certain body part. So if you look at the figure at the right, it says wrist, hand, fingers at the top. Each one of those regions, if you look at the fingers area, for example, this is a region that is responsible for sending commands that will go from the brain to the spine, to the arm, to your fingers to move. So if you decide, for example, to type your username, you would think of it in the frontal lobe, and then you will remember, you will recall from using an encoding from the temporal lobe your password, and then you would like to type it. So the frontal lobe tells the motor cortex, type this. So to type, the fingers has to move. Who is sending the commands to start moving the fingers? It's actually this area in the motor cortex, okay? So if we record from this area, we know the intended motion. We know what the user intends to move. If the user is completely paralyzed, like the lady I was showing you an image for before, or the guy who is actually on a wheelchair, and we would like to capture the intended motion, we need to record from these areas. Similarly, if you have an EEG headset for playing games, a BCI headset for playing games, well, if in playing a game, you're actually moving your body organs. Now, how is the motion initiated? It is initiated from the motor cortex. That's why you will see all headsets, commercial headsets for playing games, will be recording from the motor cortex. Okay? Now, the width of the area here has significance. If you notice, for example, the fingers area is quite big compared to, say, the elbow area. Why? Because with your fingers, you have very fine dexterity. You can move your fingers and do very fine movements, okay? While with your elbow or shoulders or trunk or hip, how many ways you can move it? How many ways you can move your shoulder? It's probably very limited. So the size of the area tells you how fine resolution you can actually do something, do a motion. That's why if you look at your tongue, for example, area, you said it's quite big because you can actually move your tongue in quite a number of amazing ways. Okay, and you can push it to the front, roll it to the back. You don't really get a sense of that because you're taught how to speak when you're very young to produce the sounds of the language, whether it's Arabic or English or whatever, and for that, the organ itself has to be movable, with enough resolution, and actually it is actually quite fine resolution, as you see, because of the size of the area. Same thing for your chewing, for example. When you swallow something, it's a very complex process that you do in your chewing and swallowing, that you do in your body. There's a number of muscles that you move to expand your esophagus to be able to swallow anything. So again, the area is relatively big. Okay. So now you've learned something. You know that the lady who was eating the chocolate bar, I told you she had an implant. The implant actually was on the top of the hands and fingers areas. Okay. Why did they use an implant? Because from the skull, from the outside, you can still record, but it's not fine resolution, because you have the skull, and the skull has a number of layers, the epidermis for the skin and so on. If you really want to see like the real thing, then make a hole and drill in the brain, in the skull, and put the chip on the top of touching the fingers area. That's exactly what they did. Okay, but obviously computer scientists are not allowed to do that. I hope you'll never make a drill in anyone's brain. You need to be a qualified medical doctor to actually install such a chip in someone's brain. Now, I told you that we have different areas in the brain. So here is a specialization map that shows which area is associated with which activity. So for example, if you're writing, that's the writing area. If you're reflecting on or making a judgment, that's another area. Okay. If you are listening to music, certain area will be activated. Okay. If you're reading, another area will be activated. Okay. The 10-20 montage I was referring to earlier is displayed here clearly, and it is actually labeled by the lobe you are recording from. So F stands for frontal lobe, okay? C stands for central sulcus. CP is between the central and the parietal, so a centroparietal. P is parietal, and it goes like this. O is occipital, okay? And there is a number of versions from the 10-20 montage, okay? The most comprehensive version would have 128 electrodes, okay? That's a lot. In HCI and in BCI, we don't need 120 electrodes. And there's 64 electrodes, and there's 32 electrodes, and there is 18 electrodes, and there is 16 electrodes, and so on. There is 8 electrodes. So the point is, you don't have to record from all the electrodes, depending on your task. Okay. So for example, all the headsets for games, okay, will only pick ones that are relevant to motion and thinking about motion, or related to understanding how much the user is stressed. So they would typically record from the C's and some of the CPs and some of the FCs. FCs is between front to central, so it's between the frontal and the central. Okay, so you could design a headset just for the electrodes you are interested in. Now, how do we get these areas? This is how did we discover them? Well, scientists, specifically neurophysiologists and cognitive scientists, cognitive psychologists, will run experiments, will do EEG recording, and will give the user a task. And during the task, they will measure from the different electrodes, and the electrodes that shows most activity will be the one that's associated with this task. Now, if you really think deep about what I just said, there's obviously an issue that this is not that detailed. This is not giving us detailed insight into the brain, okay? Which is indeed true. We are recording from the skull, but we know that that area was showing activity. How far deep down in the brain it was showing activity, we cannot know with EEG, because EEG always records from the surface. There are other techniques that I don't cover in this course, like MEG and fMRI, that actually can go and give you a better picture of the dimensionality of the activity. How far deep, how far to the right, how far to the left it's actually the area is active. Okay, so here, for example, you see an image I got from a study. Users were listening to passively viewing words, listening to words, speaking words, generating verbs, and you see different areas are getting active. Of course, there is some kind of overlap, like for example, when they spoke words versus generating verbs, there is an area that seems to be common in both, but also there are differences. Okay, so there are hundreds and hundreds of these studies. They get a bunch of users, give them a task, record, and then publish a paper saying, okay, when the user is doing this, this is the area that's active in the brain. And when a number of research works agree on the finding a specific area for a specific task, okay, then it becomes accepted universally that, okay, this is the area responsible for this task. This is another example of what I was mentioning. Okay, here is a number of processing of numbers experiment was done. There is a variation of the numbers. You have viewing numbers, processing Arabic digits, which is the digits used in the computers. Okay, nowadays, like the ones you see on your keyboard. Okay, comparison between Arabic digits, movement between Arabic digits, error correction between Arabic digits, and consequently, we isolate where is the processing of numbers happening in the brain. Now, another thing also you need to be aware of when we talk about the brain is that we have what's called lateralization of the brain activity, which means for most tasks, either the left side or the right side is actually active. Now, the brain has two sides, as you probably already know from your biology course. There is the right hemisphere and the left hemisphere, okay? And it's very rare to actually see an activity that causes activation of the two sides at the same time, okay? As it's said out here, if you look at the left hemisphere, it's associated with language skills, analytical time sequence processing, and so on. If you look at the right hemisphere, it's associated more with expressing emotions, reading emotions, understanding of metaphors, okay, reading faces, and so on, okay? Even at the emotions level, most negative emotions that you feel are right hemisphere emotions, while most positive emotions will be in the left hemisphere, okay? Now, this lateralization is extremely important because if you're designing an EEG headset, if you know which hemisphere will be more active, then you will allocate more electrodes over there. So let's talk about conducting a simple EEG experiment. I've already mentioned to two of you, the one that was referring to the numbers and the other one that was referring to the reading of verbs and words, or processing of words and verbs. You need to understand that what we are actually doing is we are comparing the state of the user between setting idle, doing nothing, and engaging him in the task that we are doing the experiment for. Setting idle, doing nothing is called a baseline. And that is important because in the baseline, the user is not supposed to be thinking of anything. So when you give him a task and you see a difference in the brain signal, you're comparing it to the baseline. But if you don't have a baseline, you don't know what you're recording. Is this the normal that the user is always experiencing, or is it because of the task that you've given him? Okay. Now, once we collect the data, there are 4 types of EEG analysis activity that we must do. Okay, and each type is covering something interesting about the brain signature for the given task that we are studying. Okay, now these are the 4 types. We're going to analyze the power. I already mentioned that before, that for every band we're going to figure out the power. We're going to also do something called coherence analysis. We're going to do symmetry analysis, and we're going to do loop analysis, which is just another way to do the power analysis. So the first step, as I mentioned before, when we read EEG data or record EEG data, which is just going to be positive and negative numbers, okay, going up and down from every electrode, is to do signal decomposition. Okay, and each, as I mentioned before, frequency power will be calculated so that we can talk about the power of alpha or the power of delta or the power of theta and so on. Okay, so that's what's called power analysis. Now, we need to understand that the brain is very, very complex. So when we record from it, we're not going to record for hours, because it's so complex that all kind of things could happen. And if you record for an extended period of time, the signals will cancel each other. So when you try to find something unique, you will not find anything unique in the signal. So usually the recordings is going to be short duration, what's called epochs, that will last for a very short period of time. Or you could record for a very long period of time, but then you actually pick the epochs to be 4 or 5 snapshots that you take from the long recording, and that's what you work with. Okay, now remember, we're talking about a recording that could have relatively high resolution, because if you're doing sampling of signals, you could go to 128 or 256 samples per second. So if you record for like an hour, that's like a lot of data. And if you have even like 15 electrodes, that's still like a lot of data. From one electrode, if you have a sample rate of 256, which means every second you take 256 samples, you multiply that by how many seconds exist in an hour, and if you're recording, say, while the user is sleeping for like 4 hours, that's like a lot of numbers. Okay, so what we do is we take what's called epochs, which is short durations of recordings, usually 3 to 4 minutes at most. Sometimes it's even less than that, and this is what we do the analysis on. Okay, now what we are going to do is we're going to do power analysis per electrode. So for every electrode, if I have 15 electrodes, let's say from F1 to F9 and from C1 to C6, I will produce a power number for every band and every electrode. Okay, this is what all EEG is about. This is what all BCI is about. Okay, in no way can I understand what the user is thinking of. It's just some numbers that represent the power, how much or how strong some band is. So I'm saying this explicitly because if the next time you read in the news that in the future people will be able to hack through your brain and get information from inside your brain, for sure it's not going to be done using EEG, and for sure it's not going to be done using any technology that currently exists. Okay, all what we can using EEG is to record some power values, which tells you how strong this band is, and that's all. Okay, now what we'll be interested in terms of EEG is, or brain recording, is to find a difference from the baseline when the user was sitting still, because we would like to know which electrode is showing a change, a statistically significant change, a real change from the baseline. Okay, so obviously anyone who claimed to be doing anything with brain-computer interfaces must have done an experiment, must have figured out where is the electrode that is showing the change, which electrode is showing the change, and how much is the change. And then they would give you a solution, like, okay, if you would like to know if the user is feeling stressed, then record from this electrode, say F9, and see if the band of theta changed from 30% to 15%, then you know he's stressed. This is actually what the experiment that was done, or the game that was done, the brain ball was trying to do. They used one electrode, they put it at the frontal lobe, at the front of the head. They measured from a specific location that is known to show a change in the theta, alpha, and beta in under stress. So if the theta, alpha, and beta changed in the way that was found by earlier researchers, they would assume that, okay, the user is under stress. And usually he is, because these things are very solid and applicable to all humans. So once the stress level decreases, they make the ball move towards him. If the stress level increases, they make the ball move away from him. And they were doing it for both sides, so they would know which one is more stressed by the changes in delta, theta, and alpha. Sorry, beta, theta, and beta, theta, yeah, beta and theta, sorry. Yeah, I'm confused. Thank you. Okay, so if you look at any BCI paper, what you actually see is something that looks like this. For every electrode, for every participant, what was the baseline of the delta power? What was the condition of the delta power? Okay, and this goes on for the 5 bands. What was the baseline for the theta power? What was the condition 1? Condition 1 is the task that you're going to give him. What's the condition 1 for the theta power? So you will have basically for each of the 5 bands 2 numbers for every electrode, for every participant. Okay, and then you will do statistical analysis. We'll cover that later on in the course, how you do statistical analysis of experiment data, but this is what's all BCI is about. Okay, now one thing that is important to report when you are actually presenting the results, or it's important to look for when you're reading the results of any EEG study, is what's called the relative power, or the power ratio. What's the issue here? The issue is, if you look at the table at the bottom right of the screen, it has 2 sections, log power and power ratio. Okay, now log power, between the baseline and condition 1, the numbers are reported, which is the average plus the standard deviation, plus or minus the standard deviation. So for the delta, for example, it was 0.65 plus or minus 0.14, and then in condition 1 it increased, it became 0.97 plus or minus 0.13. Okay, and the same thing for the theta, alpha, beta, and gamma. But there is an issue here, which is this does not tell you how much the delta was from the total in the baseline, and how much it became from the total in condition 1. Condition 1 here refers to any task you give to the user. Okay, so we would often also report the power ratio, which is the change of the delta, or the percentage of the delta from the total power in the baseline, and the percentage of the delta from the total power in condition 1. And as you notice, yeah, if you look up in the second line, it says 0.65, 0.97. It's an increase of 37%. That's very interesting. Okay, but if you go down after the line that says power ratio, delta was 0.78 from the total power as a percentage, and it increased to be 1.01, which means delta is not really significant. Okay, now why this is important, these power ratios? It tells you something, because you're not supposed to see lots of delta while the person is awake, unless he has some kind of brain tumor, or he's mentally ill, he has some kind of illness, like he's getting seizures or whatever. So it's important to report the power ratios. Okay, in fact, if I ask you here, what was the user experiencing? Now, we said before that the speed of oscillation is related to the intensity of activity. So if you're doing a math exam, if you remember, what's the worst exam you had in the university? Maybe a differential equations exam. Okay, now you were really stressed, and in that exam, your brain will be seeing, will have a lot of gamma. So the more stressed you are, the higher the frequency of the waves. In fact, when you wake up in the morning, you're often feeling drowsy while sitting at bed. And when you were asleep, it was delta. When you start to wake up or you're sitting drowsy in your bed, you're probably experiencing theta waves in your brain in most of the locations. When you leave your bed and decide to wake up and you're standing maybe in the washroom, or you're just looking around, walking slowly at your house, preparing a cup of coffee or tea, you're probably in the alpha. Okay. When you go to your car and you're becoming alert because you could hit someone or someone could hit you while you're driving, you will be in certain times in the beta. So the more stressed you are, the faster, or the more you're engaged mentally, I would say, not just stressed. The more you're engaged mentally, the faster the brain wave, or the higher the frequency. Okay. So if you look here, and this is all what we can do with EEG. Really, this is a typical result coming out from an EEG study. Okay, just that we can spell science from fiction. All what you can claim here is that if you look at the delta at the power ratio, it was 0.78 and increased to 1.0, and then in the theta it was 2.07 and it increased to 2.92, and then in the alpha it was 40 and increased to 49, and in the beta it decreased to 45, and in the gamma it also decreased. So what this means is the guy was in the baseline doing nothing, and whatever he was doing in condition 1 was getting him even more relaxed, because we are seeing less and less of beta and gamma, and we're seeing more of the slow waves, the delta, theta, and alpha, which means he's getting relaxed. So he might have been, for example, meditating or taking a massage or something, okay? Because he's getting relaxed even more than the baseline. And the baseline is supposed to be not mentally occupied by anything. He's supposed to be sitting still. So if you do an activity where the delta, theta, alpha increases from the baseline, that means you're making him more relaxed, more happy, perhaps. Okay. So this is what we do in EEG. This is what we do in brain-computer interfaces. Okay. We can just make such a claim because of the numbers in front of us. Okay. Now another way to present the power findings instead of the numbers that we were just looking at is to produce what's called a heat map, where the most power found, or the biggest power found in an area, is colored with red, and then blue is considered like the cold or the lowest power, and then you have a kind of a grade of color changes from red, the highest power, to blue, the smallest power. Okay, so it's just a visualization technique. You will often find it in papers, to enable us to quickly spot where is the highest power, or the area in the brain that has the highest activity. What else do we do? We also do coherence analysis. Why do we do coherence analysis? Because the centers in the brain are not isolated from each others. They communicate with each other. For example, I already mentioned that when you look at something, the eye communicates information through the optic nerve to the occipital lobe. But the occipital lobe actually does not make sense of things. It's the frontal lobe. So the center in the occipital lobe, or one of the centers of the occipital lobe, must communicate with some center in the frontal lobe. Now, coherence analysis will reveal which areas in the brain are working together, or which centers in the brain are working together. Now, usually when they work together, they will be running at the same pace, because if they are feeding in input and output to each other, in order not to miss any input or not to miss any output from one side or the other, they will have to sync somehow how they are actually working. And when we do coherence analysis, we uncover such a relation between different centers. What this means is that if I'm recording from 15 electrodes and I'm trying to figure out which one are coherent, I have to test all combinations. Electrode 1 was electrode 2, electrode 2 was electrode 3, electrode 1 was electrode 3, electrode 3 was electrode 4, electrode 2 was electrode 4, and goes like this until I found that one that is actually, or the pair that are coherent. Okay? And I could end up discovering more than two. Okay? I could end up discovering that maybe electrode 1, electrode 2, and electrode 3, and electrode 7 are all communicating together. And this becomes the signature that we're looking for an activity. It's not that there is a change in the power as much as that once the task starts, they get locked into some power or some power range, and then they become coherent with each other. They're now sending back and forth information as if people are talking to each other. So as I mentioned, we are going to calculate what's called coherence between every two electrodes or pairs, and we will do that for every band. Okay, so this is going to be, actually, if you do it for real, it's going to be a really big table. It will just have, for every band, that we have 5 bands, and if we have 5 electrodes, then for every one of the bands, I will calculate all the pairs. So electrode 1 was 2, 1 was 3, 1 was 4, 1 was 5, and then 2 was 3, 2 was 4, 2 was 5, and then 3 was 4, 3 was 5, and then 4 was 5. That's just for the delta. And then I will repeat that 5 times, delta, theta, alpha, beta, gamma. Okay? And I will do that for every participant that I recorded from. I will not really go into the math of how do we calculate the coherence between two signals. I will leave that to the brain-computer interface course, the BCI course, which I teach later on in another semester. But if you're interested and you have not seen this before, then check out this Wikipedia article, but it's not part of the course content. But what I want you to understand is this is another important activity and another insightful piece of information that we can do with EEG. Okay? We know which centers are working together, and that's basically it. Now, in the literature, you will often find charts like this that tells you which pair was working with which pair. Okay? So instead of listing them as a table, researchers would often display or produce a printout of the montage they use, and then they would put marks that tells you these guys were working together, okay, for a specific task. Now I want you to look at this chart and tell me if there is anything interesting from your perspective given what we have discussed up till now. I'm just going to give you a few seconds and then you tell me. If you haven't figured it out, here is what's going on. I've already told you that most brain activity are lateralized. Either the left lobe is active and working more than the right lobe, or the right lobe is more active and working more than the left lobe. What you actually see here is a special kind of task that involved a lot of coherence between right and left lobe, which is quite uncommon. Very few tasks actually produce such a signature, okay, where you see electrode pairs from both sides working together so intensely, okay? So this is really the finding here. Now, a third type of analysis that we could do with EEG data is symmetry analysis. I already mentioned that lateralization is an important feature of the brain. But if you actually do coherence analysis and it turns out that there is a lot of information exchange between electrodes residing on the different hemispheres, left versus right, then what you could do is symmetry analysis. You analyze the symmetry between the actions happening or the recordings you get from the right hemisphere compared to the left hemisphere. Okay? Now, this will give you kind of even a more bird's eye view of what's happening in the brain, because you will look at the whole lobe as one, at the whole hemisphere, at the whole right hemisphere, for example, as one organ compared to the left hemisphere as another organ, and you try to figure out how much they were expressing symmetry or asymmetry. Okay, and this has been found to be a signature of certain tasks. Okay, for example, when people lie, it has been noted that there is a high degree of asymmetry between the two sides. Okay, and you would report that, as it shows here, in a table for every band. We always work with every band separately, so we always process delta information separately and then theta information separately, and so on. There are many ways to calculate asymmetry. One of the very popular ones is left power plus right power divided by left power, and this is applicable per band, so it's going to be left delta plus right delta divided by left delta. Okay, this is just one way to do it. There are other ways, but this is popular and it has shown to produce always positive results when there was indeed some kind of symmetry witnessed in the study itself, perhaps earlier through coherence analysis. Now, a further type of analysis we could do to the EEG data is to look at every lobe and compare it to another lobe. We said there are 4 main lobes in the brain, and we would be interested sometimes to compare what's happening in totality for a number of electrodes that reside in the same lobe. So we would compare the frontal lobe versus the parietal versus the temporal, and so on. Okay. Again, all these types of analysis. First, I'm trying to give you an in-depth knowledge of what we can do, and I want to highlight the fact that we are still far away from understanding how people think. Okay. As you see, all these analyses are very primitive. They're all basically working with numbers. There is no notion of I know how to extract a user password from his brain, or how can I extract his memories, or perhaps even better, how can I augment his memories? Okay, so I can maybe download a textbook to someone's brain, so he doesn't have to study. He can just go to the machine and download the textbook, and that's it. Okay, nothing of what I have described up to now, and what I'm telling you are the basics of how people work, and this is how research is done, by the way. What you can do with the brain. Okay, you can calculate power, you can find coherence, you can find symmetry between right and left hemisphere, or you can do lobe analysis. Okay, so you'll end up with something like in the following slide. So this is what you do. Okay, you say, okay, for each one of the lobes, you see it listed at the left of the bottom image: frontal, central, temporal, parietal, parietal central, parietal, and occipital. You say, okay, this was my baseline in total for all the electrodes there, compared to condition 1, which is the user was doing something. Okay, so you could say, okay, in the frontal lobe I witnessed more alpha, or I've witnessed more delta. Okay, that's basically it. That's all we can do. Okay, just a bunch of numbers telling us about the fluctuation of the electrical current we're recording. So the takeaway is that there are 4 types of EEG analysis: power, coherence, symmetry, and region/lobe. Now let's come to our next topic, which is event-related potentials, and this is really what many BCI works would use. Okay, so what I have been describing up to now is kind of the advanced BCI works. Like if you're really reading a cutting-edge BCI work, they would be doing what I just described. But what is the standard way of working in BCI, in brain-computer interfaces? The standard way of working is to use ERPs, event-related potentials, and these are even more simpler and more naive than anything you could imagine. Okay. Now, what is ERPs? Let's start. What's an event-related potential? Okay. It turns out that our brain, in response to a certain stimulus, to something very specific, okay, certain event, if you'd like, would produce, for an unknown reason, a very naive, simple, primitive signal. You could even think of it as a deflection in the signal in a very specific location. Okay? So with all the complexity of the human brain, you should be surprised that this is actually the case. Okay? So for example, if you hear a sentence that does not make sense. Let's say, for example, someone is telling you, I had a great breakfast. I ate my bicycle. The minute you hear something that does not make sense in a certain region in your brain that we know of actually, there will be a very short duration signal with very known clear characteristics will occur. It has been theorized that these signals, which is ERPs, that's why they're called event-related, because they are related to the event. Potential means potential change. So these ERPs are the resultant from millions of neurons working together, and somehow they add up to the same number or same value, and that's why this deflection in the signal would happen. Okay? And there isn't many of them, they're just a handful. And they are used heavily historically wise, history wise, in the BCI works because they are so simple to detect. In fact, they are so naive and so simple. You don't have to do anything of what I have described earlier. You don't have to do power analysis. You don't have to do EEG analysis, loop, symmetry, coherence. You have to do nothing. You just present the stimulus to the user, present the event to the user, or put the user in the context of the event, and just look for the signal in the EEG recording that you're making directly. The first ERP we're going to look at is the P200. Now, all ERPs are named P or N for positive or negative, and then a number that signifies how many milliseconds the ERP or the signal will appear after you have shown the user the stimulus or put him in context that is supposedly going to invoke the ERP in his brain. So P200 means a positive signal appearing 200 milliseconds on average after the stimulus, after the presentation of the cue that will result in the ERP. So it will range in temporality from 150 milliseconds to 275. So on average, it's 200 milliseconds. Okay? Where will it appear? It will appear around centrofrontal and parieto-occipital regions. Remember from the montage, we had electrodes there, the CFs and the POs. So if you would like to look for it, you just record from these locations. Now, what would make it appear? It is a reaction to a change in the visual stimuli. Let's say, for example, you're designing a BCI system to monitor the user behavior or the user state, and an important message has arrived and the user is working on the desktop, and you display the message at the bottom right of the screen. If the user saw the message, immediately after it, by 200 milliseconds, a P200 will be recorded. Now, it could be that, obviously here's the problem, it could be that some other change happened in the user interface, and that's why you're seeing the P200. But if there is no other change happened in the interface, the only reason why you would see a P200 because he noticed a change in the display, that there is a message popping up from the bottom right of the screen. Okay? So, how do you design for invoking the P200? Any change in the color, size, or orientation of the stimulus will invoke the P200. Okay? Now, why does it exist? Now, perceptual psychologists would argue that there is some kind of a matching system that happens all the time in the brain that tells the user about the surrounding environment. And when a change happens, the change is first detected by that matching system. It's as if you're always recording what you're seeing, and when you see a difference, the previous frame from the current frame, you recognize the difference. What they theorize is that this process that recognizes the difference between the visual frames or the visual cues is somehow resulting in the P200 signal. Okay? So it would always be argued that this is a high level processing of information because you are not really following the details. It's not about a minor change in what is you're perceiving, but it is more of that the display changed somehow. So that's why it's called a higher level order or a higher order processing, okay, of events. Okay, now this has been used by perceptual psychologists when studying visual search tasks, okay, when studying also attention and language and memory. For us in HCI, visual search is probably the most interesting. If you would like to display something to the user, as I mentioned before, and make sure that he actually can notice it, then you can use this as a proof that he noticed it. if it shows up, if everything else is fixed. Now let's see another one, the P300. This is the most famous one actually. This is a positive signal that appears 300 milliseconds after a stimulus. Obviously it has a higher temporality here as what's stated in the first bullet. It can show up anywhere from 250 milliseconds to 500 milliseconds after the stimulus or the cue. Okay? It's strongest over the parietal and frontal lobe. So this is where it often appears and it can be clearly detected. Now, this is a little bit funny, so let me explain it slowly because this is the most important one. What happens in the brain to invoke this guy? Cognitive psychologists would tell you, well, it actually reflects that there is some kind of a process in the brain that always tries to evaluate what is the user is currently seeing, and perhaps this evaluation is related to categorization of that. But at the minimum, it is related to evaluation of what the user is perceiving. And as a result of this evaluation, the question becomes, as a personal question the user has in mind, is this important to me or not? Okay? Now, I know this sounds like a little bit high level, but just wait, this will get really interesting. So, how we design for the P300, okay? Since this is related to the user evaluating what is currently present, then we have to play it in a way so that the user evaluation was not interesting and then suddenly I'm interested. Okay? Because if this is related to evaluation and it gets invoked when the importance of the situation changes, then we have to follow a design that goes not important, not important, not important, not important, oh, important. So now we get the P300. Okay? Now I'm showing you here in this slide also what would it look like without the target stimulus, without the stimulus, without the cue that will invoke the P300. You can see the fluctuation, the red fluctuation is very normal, typical, EEG. With the stimulus or the cue that will invoke the P300, you can see the cusp that says, P300, okay? The stimulus is, there is a stimulus onset. This is when actually the cue or the event happens that will trigger the P300. And you can count 300 milliseconds on average, and you can see that the P300 is appearing. It's a positive signal above the zero, and it goes all the way in amplitude, and it's a little bit wider than the other signals, okay, in terms of the wavelengths. Now, why this is the most popular one? It has so many applications. It has been actually used in lie detection, has been used by intelligence agencies around the world. It has been used by BCI, in BCI systems in many applications. The most famous one obviously is the BCI speller, and it has been used in other things as well. Okay, so let me show you what is this all about. So here's an example of using the P300. This is the same speller I have discussed with you before. The idea here is that the user would type without using a keyboard by looking at the characters, and in the popular media they would say that the user is typing, or the system is detecting what the user is thinking of and typing the letter for him, which is entirely false. Here is what's happening. What BCI spellers do is they make use of the P300. The P300 basically is present the user with a change that he needs, followed by an absence of the event he needs. Let me give you a naive example. Let's say you're working on a project and you have a colleague whose name is Ahmed, and you have been in dire need to meet Ahmed to get some source code from him or to share some project insights. And for some reason, you and Ahmed couldn't meet for 4 or 5 days. And you really need to talk to him because you have this great idea that will simplify the amount of work you have to do for a specific project. So you're sitting in a class and the door of the class is made of glass, so you can see anyone who is passing outside. So you're sitting and concentrating in the lecture, and you're also seeing people passing by the classroom. You can see them through the door. And suddenly you see Ahmed. So you go, oh, Ahmed. But Ahmed doesn't know that you're actually inside the class. So he keeps walking. So you saw Ahmed, so you say, oh, Ahmed, and then Ahmed disappears. Okay? This is what's called, in psychology, the oddball paradigm. It's like you see it, oh, I want it, oh, it's not there anymore. Okay? So in order to invoke the P300, the way the BCI speller works is as follows. The letters will flicker quickly, horizontally and vertically, as you will see in the video. So all the line that starts from a D and goes all the way till 8 will flicker in one shot. And then following this vertical line flickering, there will be a horizontal line flickering. For example, the lines that starts from S and ends at X. And this is happening very quickly. If the user would like to type something, like let's for example here what shows up, he's supposed to type hands-free. Now what's between the brackets afterwards is the current letter he's supposed to think of. So he just typed the F and then now he's supposed to think of the R. He's supposed to look for that letter and wait until the horizontal and vertical flickering intersect at the R. And that will happen because all the letters are being intersected by the two lines of flickering, horizontal and vertical. So when the horizontal line and the vertical line intersect flickering one after the other at the R, that's what he wants, that's what he is thinking of. But within milliseconds afterwards, another letter will be intersected by the horizontal and vertical line. So he wanted R, but immediately he lost it because another one now is at the intersection of the two flickering lines. And for that, a P300 will be induced. For that reason, a P300 will be induced. Once we see the P300 in the recording, we will go back 300 milliseconds and see which character was being highlighted by the horizontal and vertical lines, and it happens to be the R, so we insert an R. So we have really, if you think of it, we really don't know what he's thinking of. It's just we know that when he misses what he's thinking of, we're going to see the P300, which means we're going to see a positive deflection in the signal 300 milliseconds after what he wanted. But we don't know what he wanted. We just know that it exists 300 milliseconds away from us when we see that P300. So we go back and find that time, and then we go to the software and figure out from the recording of what's being played what was the letter at intersection then, and it turns to be the R, so actually we insert the R. Okay? Now the question is, I want you to watch the video that I have linked here in YouTube, and the question is going to be to you, is this fast? And actually when you watch the video you will discover it is actually quite slow. Why? Because the flickering has to happen so fast so that we get the P300. If the flickering is too slow, when he sees the R, and if we're doing the flickering or the intersection of the vertical and horizontal line too slow, we won't see the P300 in his brain. because he will see the R being at the intersection, and he will spend time looking at the R being at the intersection of the vertical and horizontal line. So he's confident now that he got the R, but we want him to miss it. This is the oddball paradigm. We want him, oh, you want that? Okay, here it is. Oh, now you missed it. So it's like, oh, I wanted that. So to get this effect, the flickering has to be fast. But when the flickering is fast, he will not see every intersection of a character. Okay, so it is slow. So he might actually miss the R one point and then get it the next time. Plus, since we're intersecting with all of these options, the next time you go to the R is going to be after a while. So if he misses the next time, if he misses the first time and then he misses the next time, then maybe he will get it in the third time. But between the first and the second time to intersect at the R, and between the second and the third time to intersect at the R, we're actually going through the other letters. So generally it is a slow technique, but it's interesting for someone who's completely paralyzed, because they can wait. I mean, what else can they do? Otherwise they cannot type. Okay? But if you're interested in using this as an alternative to a keyboard, obviously it is too slow. Okay? Now, you could enhance the performance a bit by decreasing the number of options. Here we're displaying the alphabet and the digits. But for example, if you're playing a computer game, perhaps it's going to be a little bit faster. It's actually going to be a little bit faster because you will just display right, left, forward, backward. So you only have 4 options. So you're flickering between 4 options, not as many as what's in here. Another ERP is the P600. It appears on average 600 milliseconds after the onset of a stimulus, mostly on the top of the centroparietal and frontal lobes, and it is related to the hearing and reading of grammatical errors. How do you design for it? Well, you could use structure violations in a specific sentence, or you could introduce disagreement in the sentence components. Like, for example, you look at the third point, I have a number of examples. The broker persuaded to sell the stock was told. Okay, the structure here violate basic principles of even common sense. Okay, or as a breakfast I ate my bicycle. Whenever you hear anything like that, there is a P600 appearing somewhere in your frontal lobe. Okay, now this has been used by linguistics, cognitive psychologists to evaluate how fast a participant or a user or a human being detects errors in the language, whether read or spoken. So the takeaway is that an ERP is a primitive signal that is evoked due to an external event. They are the easiest to evoke and detect. And when you're building a BCI system, you should always consider them first. And you have to realize that most BCI systems are built around them, built to use them. The reason why is it's fairly easy to extract this very simple signal compared to doing a typical EEG exercise where you go record, do signal decomposition to get the power of delta, alpha, beta, theta, and gamma, do the 4 types of analysis we discussed to be able to reach the conclusion whether a signature exists or not. But on the other hand, you have a problem. The problem is ERPs are too primitive. They're not telling you pretty much anything. So you have to set up the environment or the system so that you can invoke the ERP. And once you invoke it, you decide what to do. But it's not really helping you on understanding anything about the user in terms of what happens inside his brain. Is he stressed or not? Is he happy or not? There's very few things you can do with them. But the point is, it is so easy if you can actually get away with building a system around them, especially the P300, okay? Then you can get a brain-computer interface designed and implemented super fast and super easy. Now let's talk about some of the recent research that made a sensation on the internet and in the news. You could have seen probably this in either CNN or NBC. This was a few years back. I've linked here the article that first reported it, and then, or at least that first made it very popular. This was like almost 12 years ago. A Japanese scientist, Professor Kamitani, what he did is he conducted an EEG experiment in which he used the EEG recording to try to capture the encoding of letters and decoding of letters from the human brain directly. Remember, we said that the temporal lobe is responsible for encoding and decoding of information. In other words, when you would like to store the information, it goes through the temporal lobe, it gets encoded and then sent to the storage. When you'd like to retrieve the information, it's retrieved from the storage and then decoded and sent maybe to the frontal lobe. So he tried to work on that area to capture the encoding and decoding. What you see here is the result of the experiment, which is he displayed the word neuron to the user, and the image at the bottom was supposedly from the user brain. Okay? This was the first experiment that did something like this, and obviously this was sensational because people started thinking, oh, they're going to design machines, maybe install it in the top of a door in a mall or whatever, and they will capture my passwords or my bank account information and so on, okay? Which is completely untrue. Now, another work that kind of made it even more sensational is this one. This is Professor Jack Gallant, very, very famous professor in Berkeley, and he did a similar experiment. In each one of those images, what you see on the left is the image that was presented to the user, or the clip. It's a video clip, and on the right was what was constructed from the brain. Okay, so it looks again very impressive, even though the resolution is not that good, but it looks like actually these guys are getting images from the brain. Okay, so what's the truth here? Okay, the truth is simply that this information is not being extracted from the brain in the way you would think of it. Okay, why? The brain is extremely complex and dense organ. We're talking about a very small organ, okay? It's about 1 kilogram on average in weight. It has 1 billion neurons, and every neuron, as I mentioned before, has on average 10,000 connections to neighboring neurons. All this is an area that is occupying almost half the volume of your head, or a little bit more. Now, we don't have a device that records whether spatially or temporally. Temporally means in time, spatially means in space and volume. We don't have a device that records spatially or temporally that will enable us to capture every single change in every single neuron in the brain. So the notion that they are extracting these images directly from the brain is simply not true. What you're looking at is an exercise in machine learning and data analytics, which is still producing extremely impressive results. Okay, it's a huge step forward in studying the human brain and in using the information recorded from human brains. But it is not like we're peeking inside a human brain. Okay, this is what's going on. So this is nothing but a machine learning exercise. Now let's talk a little bit about how you do machine learning. Machine learning means you ask the machine to learn. And how you do that? You collect a data set, and using an algorithm, you train on the data set. The output of the training is what's called usually a model. The model is used later on to make decisions or classifications regarding anything it receives. So let's say, for example, you captured pictures of the following: a pencil, a ruler, a cup, and a mouse. So if you would like to build in the computer the ability to detect between a pencil, a ruler, a mouse, and a cup, you take lots and lots of images of pencils, lots and lots of images of cups, lots and lots of images of mices, lots and lots of images of rulers, and you introduced every one of those sets. We have 4 sets: a set of pencils, a set of mices, a set of rulers, a set of cups. You introduce it into a machine learning engine, and you put a label on every set. You said, all these are pictures of pencils, all these are pictures of mices, all these are pictures of rulers, and all these are pictures of cups. The machine learning engine will try to figure out what is, using statistics and math, what is different numerically between every one of those sets. And after a while, it will come back and tell you, maybe the learning will take few hours or few days even, will tell you, okay, now I have learned something about how to differentiate between any one of those 4 objects. The output of that is the model that will be used in the later on classification, okay? So the output of the learning is what's called model, a classifying model. Now later on you go, okay, you tell it, Mr. Computer, you know now what is a cup, what's a ruler, what's a mice, what's a pencil. I'm going to show you a picture and you tell me, what is this? So you input to it a new picture. Let's say it's of a pencil. So it goes and matches in the graph model it has built the properties of the image that you've passed with the details of the model. So it will tell you with certainty, with probability, 90% this is a pencil, 10% it's a cup, 5% it's a mice, and so on. Okay? This is what all machine learning is about. And this is what these researchers did. Okay? What they did is they have shown users images, many users, many images, and they have recorded what was inside the user brain using brain recording devices, what was then inside the brain. But they have no notion of the what each neuron is doing. It's just a holistic picture. It's a total picture. It's not about the particular detail. It's like, this is the state of the brain now when he's looking at this movie, okay, at this frame, at this movie, okay? And they collected a huge data set, okay? Now, later on, they could ask questions like, what is this picture looks like? So it looks like, a dog, it looks like a house, it looks like a cat, and so on, okay? So these works are really exercise in machine learning, and it kind of stresses the importance now of machine learning, because we can do this because of machine learning, okay? But it's not that we are peeking in any way into the user brain and figuring out what's inside his brain, okay? It's nothing of that. Now, the potential of brain-computer interfaces is enormous, to the point that a very respectable company like Sony, applied and got a patent that says that we can beam information to the brain. Technically, this is impossible, because we cannot direct an electromagnetic radiation to hit a very specific area, if we're going to do it that way, in a brain, to do the encoding and decoding of information, or at least the encoding of information. But they have done everything except that device in their patent, and you can read about it in this article, okay? And this is again what causes a lot of hype, because there's a lot of companies trying to capitalize on the notion of brain-computer interfaces, but the reality is we don't have devices that would do these things, okay? And some people actually would argue against this patent and say that this patent is flawed from the beginning. It should not have been awarded to Sony because it is impossible, okay? There is actually a rule associated with patents that if the US Patent Office decides that is not convinced that this patent is real, he can get the inventor and ask him to reproduce the work. And obviously, in the case of Sony, they would not have been able to reproduce the work, okay? But they got the patent, unfortunately, which caused again a lot of hype and misinformation about brain-computer interfaces. Now, brain-computer interfaces does not stop at beaming data to the brain. That's a bit fictitious, but there are studies now that are having much bigger impact on different branches of science, coming from studying the brain using EEG devices and similar technologies. Okay, I've linked for you here one application of EEG studies that argues that those who have been born into poverty, and they have stayed in poverty for generations, comparing them to someone who has stayed in luxury and high standard of living for generations, would perform cognitively better. And obviously these studies are extremely debatable, but again, without the advancement in brain recording, we wouldn't have been able to even see such kind of studies. Okay, you could think of all kinds of brain-computer interfaces applications based on the notion that we know the signature of many activities. Okay, so you could detect using a BCI headset perhaps that the user is overeating, okay, or that he needs to eat certain maybe diet. So there's a lot of research in these directions. Okay, there's also research done on the brains of criminals, those who do heinous crimes, to trying to figure out, when they were slaughtering their victims, like, how come they didn't feel any guilt? Okay, so there's lots of interesting studies done on signatures of all kinds of tasks, all kinds of activities, all kinds of people. Okay, and this opens the door for research in brain-computer interfaces. Okay, so it's not anymore like using just the ERPs to detect whether should I turn right or left. It actually will go beyond that in the future. I will show you here some sample research. This is a new area. It's still in its infancy, but it's promising. This is one piece of work that was published in a recent conference that turns the contact list into a set of images, and the user would pick the image he would like to call from the displayed images using P300. Again, the images here are flickering very quickly, so the one you actually would like to call, once you see it highlighted and then it immediately the highlighting changes and another one gets highlighted, then a P300 will be invoked in the user brain. You can detect which picture was actually highlighted 300 milliseconds ago, and you would make the phone call. Perhaps this kind of interface is most useful in a car driving context. If you're driving in a car, you don't want to hold your cell phone. If these images are displayed on the windshield, then using a P300, you will ultimately get the call done without you holding the phone. Another example here of also recently published research is the notion of using EEG accompanied with feedback to the user to control certain negative emotions they have. This specific research was done to control anger. So the user or the participant in the experiment was shown video clips of confrontational situations, and he was shown his brain reaction to the confrontational situation. Obviously here this was done on patients who have problem in controlling their anger. So they are people who get too angry too quickly. And by displaying the power of the different bands in the different electrodes used, and telling the participant to try to control how he's thinking, and displaying to him the power that he's going quickly from maybe theta to alpha to beta to gamma, and his brain is like really boiling. By displaying to him the power, he would start to control how he's thinking about the situation. Okay, this is an example of what's called neurofeedback. You record, you calculate the power, and display it to the user and tell him try to change it by thinking slower or less angry, or by being more contemplative about the situation instead of jumping to decisions and trying to take action. So this is an example again of what's called neurofeedback, and you will need to watch the video to see all the details. Now, all the videos I have linked here that is not available on YouTube is available in this link, and I also including to you an optional material to read about EEG and how it's recorded, and the details that I kind of went through in this lecture if you need further reference.